Okay, so the record is now on. So let's take a look at the detail of the work that you are given. Perhaps let's imagine yourself as an engineer. Now somebody say, okay, we need to use the H shape to carry a date load of 15 tons and live load of 45 tons. Okay, so now the information that we have is that we are going to use the H shape. And let's say the decision has been made in the beginning that we are going to use this SS400 material. So you as an engineer must know that if this is going to be your material, you must know the Fy is going to be 2,500 kilogram per square centimeter. And Fu, I still prefer to have a little bit of 50, so it's 4,050 kilogram per square centimeter. This is automatic, okay? And let's say if you fail to use the proper number here, I will be extremely critical of you because it's the criteria that you must first set right in any of your work in the future. You should always pay good attention to the fundamental of everything before you start to put your effort into the real body work. Okay. The next thing that you know is that, okay, this is going to be the load. So let's say here for the first example, we are going to try to show you work both in ASD and Lrfv. Okay, and we are going to have two conditions to demonstrate the shear lag, so to speak. Okay, so in the first condition, it says that the member is going to be entirely welded to the support. Now, when you see a condition like this, what information can you get from this condition that you have? It says here that the member is going to be entirely welded to the support. It means that we are going to weld both the flanges and the web to the support, meaning all the elements are connected, both the flanges and the web, meaning we are not going to have the shear lag problem. Okay, is that a good thing, right? So now the next step that we should do is, of course, if it's a work in the real world, it's your job to study the law. Okay, even though now somebody must have done that for you because you have the date load and live load, but what you should also make sure that you take care of is the load combination. How can you compare this load to create the worst case scenario? Okay, so let's say step number one, I can say we are going to calculate required, I don't write a full word, so that is my required, okay, required tensile strength. Now you prefer me to do the ASD entirely first and then Lrfv, or you want me to do it all together? Answer, please. Okay, please. You're catching the silent virus. Okay. So anyway, I will do both at the same time. Okay. Let's say, how's my handwriting? Can you read? That's tensile strength. Is that okay? Please tell me right away if you cannot read my handwriting.
Yeah,
that's all right. That's all right.
Okay, thank you. Please do inform me right away if you cannot read. Okay, because sometimes I cannot read mine as well. So if you leave it late, if you let time go by, and you ask me later, you will probably run into the situation where, I would spend 5 minutes looking at my own handwriting and I would tell you, I don't know. Can't read it. Okay, that happened before, believe me. So let's say if it's ASD, because we have only date load and live load, so the worst case for the load combination is going to be, now in my sheet here I say P, but please you know, my apologies. Sometimes I write T, sometimes I write R, sometimes I write P, which is the same thing. It doesn't really matter, you know. Okay, so let's say PA. ASD is the service load. You can obtain the load combination from the building act most of the time. So the PA say here that the date load and live load, you just can add them up. So for ASD, it's going to be 60 tons. Okay? Hope you don't mind that I use the ton force unit. Okay. If it's a Lrfv, it's the factored load. And you probably have seen it before. This is going to be the ultimate load. It's going to be 1.2 date load plus 1.6 live load. So that is 90 tons. Okay. So the next step that we are going to do is that now we have the load. Now remember, when you are going to design something, it means that that particular thing never existed before. So we are going to use magic to create something. So now it's time for us to do some preliminary design. So let's say for ASD. Now we know it's D, not P. Now we know we have two failure modes involved for the tension member, right? So the first one is going to be the yielding. Now, to prevent yielding, the PA that we have will not exceed our design strength. Remember, our design strength for ASD is the nominal strength divided by factor of safety. Let me write it down again here. This entire thing is the design strength. Okay, but this one itself is the nominal. All right, and now we know that the nominal strength for tensile yielding of the cross section is Fy multiplied by Ag. So this can be rewritten as Fy Ag and then divide by factor of safety. So you're good, right? So now we can rearrange this equation to calculate for the gross area. So now the gross area would become something that should be greater than the factor of safety multiplied by PA divided by Fy. Okay, so straightforward enough. Our factor of safety for yielding is 5/3, remember? PA is 60 tons, but we have to change the unit because the material properties that we use is in kilogram per square centimeter, and this is in tons. So I just multiply it by 1,000. And then I can divide this by Fy, which is 2,500. So now I get the number equal to 40 square centimeter. Okay, so straightforward enough. Please don't hesitate to ask questions if you're not sure about anything. Don't keep your doubt in your mind. Remember, folks, the worst question is the question that you never ask. Okay, there is no such thing as stupid question. Okay, so please do ask any question that you feel like you have to get it off your chest. Okay, so here we are. That's the area to prevent the tensile yielding. So if you select the area greater than this, you should take care of the yielding failure. Okay, the next is the rupture failure. Now again, PA must not be greater than the nominal strength divided by factor of safety, but this time it is going to be FUA net. Remember, we don't this time we have holes. We don't have holes. I'm sorry. We're gonna weld all the member to the support right away. So in this case, the A net is equal to the A gross, right? And so it's kind of a blunt calculation to do, but you know, you should always show your calculation for every failure mode. If you don't want to do this, you must make a statement to show that you understand that there is this kind of failure mode, but it will not govern, something like that. Okay, and when you have the net section equal to the gross section, in other words, when you don't have the holes or anything, you know, chances are, you know, the rupture should not occur before the yield. Sorry. Stupid salesperson. Ah. Okay, I'm sorry. Couldn't be helped. So we can go ahead and try to calculate this anyway. And the A net should be, you know, greater than the factor of safety multiplied by PA and then divide by FU, right? This time, remember, it's a rupture, so the factor of safety becomes 2. The load is the same, right? 60 tons. And FU this time is 4050. And this turns out to be 29.6 square centimeter. So, okay, now we have the area for yielding, we have the area for rupture. In the end, which one you should use? Can you tell me?
Yielding.
Yielding, simply because the number is greater, right? So you could see that in order to prevent rupture, you need the area only this much. But in order to prevent yielding, you need this much. So that means you're gonna have to go for the member that has the cross-sectional area not less than 40 square centimeter. Okay, are you with me so far, everyone?
Yes.
Great. All right. Cool. So now let's before we move on, let's also try to demonstrate the Lrfv as well. Okay. Yielding.
อาจารย์ครับ
Yes, sir.
The value of factor of safety is from the previous lecture, right?
Yes, it is. You can say that. I can go back and show you now, because you know, before we get these kind of numbers, there are many great people working behind the scene to come up with numbers. This is not just, okay, I like the number 2 more than number 3, so let's use factor of safety equal to 2. Not like that. Here, okay, from this page. All right. It's lacking a little bit. So, okay, takes time. Okay, here we are. Here, that's it. And remember, as engineers, you must know which number you have to use, okay? To use the wrong factor of safety is really not nice, to say the least. Okay, it's our job that we do with professional pride. So this is a basic stuff that we must get right. Okay. All right then. So now we know where this come from, and Lrfv is going to come from these two. Okay. All right. So for yielding now it becomes Pu, right? Which cannot be greater than this time. Your design strength is, sorry, this is not straight. You know, I'm kind of crazy about the line. I have to try to, okay, do it better. Phi Pn, okay? Pn is nominal again, and the Phi Pn, this entire thing is, of course, the design strength. So this term becomes Phi multiplied by Fy multiplied by Ag. And similarly, now we can calculate the Ag. It's going to be equal to Pu divided by Phi Fy. Now we have 60 tons, change the unit, and then divided by 0.9 and 2,500. Guess what, ladies and gentlemen? The number is exactly the same. See, both design philosophy give you the same cross-sectional area that you need to have. So we, before more explanation, let me move on to rupture. So similarly, Pu cannot be more than Phi Pn. This time is Phi Fu A net. So the A net must be greater than, equal to, you know what, I should change this. Okay, all right. Pu divided by Phi Fu. And this one is, again, the load is the same. And the denominator is, this is rupture, so be careful. Phi is now 0.75 and Fu is 4050. And again, ladies and gentlemen, the number is the same. So I'll come back and explain this, but let me finish the job here first. So this is the prelim concept step. So now we can say, okay, we are going to try the section that has the cross-sectional area more than 40 square centimeter. So what you can do as an engineer is you go to the steel design table and try to look at the area here, right? That's a cross-sectional area. Now we need 40. Wham, voila. That is 40.1. Is it good enough? Nobody wants to answer me. It's good enough. We need 40. That's 40.1. What would you do? Or are you just trying to find this table? Let's look at the area, right? Because we just calculate the area. So we look at the area.
It is good enough.
Yes, that should be good enough, right? Because all the factors, safety, reduction factor, and so, you know, have been included in your calculation. So there's no need to go crazy. Hey, that area is too close. I don't feel safe. Let me use this one instead, like that. A 51 should make me feel happier. You know, we have already included everything in our calculation. We need 40, so 40 is good enough, at least for me. Okay, so yes, we are going to use I run out of space anyway, that's a small thing. So we were going to try H 150 by 150 and then by 31.5. You know, keep in mind that in the construction around this country, it may be more fashionable to give the thickness of the web and the flange as well. So from time to time, they would write down like this: H150 by 150, and followed by, because the depth comes first, right? So you should follow the by TW, which is 7, and then T flange, which is 10. No, really, I tried to resist this before, you know. This would be good enough, so I only wrote down that much. Say my season, you just write it down, okay? Something like that. So yeah, fine, you know, you can write it. It's not gonna kill me or anything. But you know, the weight here should be more than enough to tell which section you really have to use, okay? But you know, let's say there's no need to just be crazy about it if somebody asks you for more information. Be kind and give it. Yes. Okay. So yeah, okay, I run out of paper. So you know, up to this point, actually, to try to say something like, okay, I'm gonna try this section is a bit silly in a way, because you pick this section based on your correct preliminary calculation. But from time to time, you know, not just from time to time, there are many times when you select your prelim section and you have to check other failure modes that you can really not investigate from the beginning. So it would be really, really nice after you have picked up your section to just say, okay, I am going to do step number 3, which is to finally calculate the tensile, the strength of my member. So, okay, it wouldn't be a bad idea to do it. So, but if you don't want to do it, just make sure that you have proper statements saying that, okay, because I have done this and I know this and this and that and blah, blah, blah. Make sure that people know that you know. Okay. So let's say ASD, we are going to check yielding. So now my, I use P, right? Okay. So for yielding, my design strength, P nominal divided by factor of safety is going to be 1200 multiplied by the area. Oh, I didn't write down here, right? The gross area is 40.1 square centimeter. Okay. So the area is this. And then factor of safety is 5/3. Notice that 5/3 is the denominator. So when you swap the fraction, it becomes 0.6, right? So from time to time, you will see from many books or something like that, that this becomes like 0.6 Fy. The old ASD specification used to give you, you know, the allowable stress equal to 1500. That comes from 0.6 Fy. Okay. So here we are going to have 60.2 tons, greater than 60. And rupture, we are going to have P nominal divided by factor of safety. That's going to be FU. multiplied by the area instantly, the effective net area is equal to the gross area because we don't have holes and we weld every element to the support. Remember very carefully to use the correct factor of safety for each failure mode. Here is 2. So that becomes 80.2 times. Way more than 60. Okay, so now the yielding is greater than the load, the rupture is greater than the load. We should have the big OK, right? Lrfv, you can guess now, it's going to be the same thing. Phi Pn, that is going to be 0.9, 2500, 40.1. That gives me 90.2 tons, greater than 90, right? So I just run out of space. Oh, okay, I forgot to say this is yielding as well. Sorry. Maybe I should move this a little bit so it looks nicer. Power of lasso thing. Huh? All right, that's yielding. And I can write yielding better this time. You know what? Maybe I can also make the proper PDF file out of this as well and give it to you from time to time. That sounds good, right? I haven't thought about that before. Anyway, rupture. Phi Pn. Now rupture, the phi is now 0.75, right? Remember to use the correct number. Here is 4050 and the area is the same. This turns out to be 122 tons, way beyond 90. So we get a big OK. So in the end, you should summarize that you are going to use H150 by 150 by 31.5 kilogram per meter. So voila, that's the end of your very first design, ladies and gentlemen. Is there any question up to this point? Is there any question up to this point?
Is it okay that I calculate only ASD?
Yes, this is just the example because in the real design, you have to make a decision on the design philosophy from the very beginning. And you should do only one of them. You don't have to do both. But right here, it's just for the sake of demonstration. So we have both approaches, see, because it's just both ASD and Lrfv. Okay?
Oh, okay,ครับ.
Any other questions? All right. Now, because you have a class with me, or maybe you have a class with other folks, you should know this. You must know this. Notice one thing. See, regardless of the method that you use, you end up, see, with the same requirement. You can see here that after the calculation of the area, turns out to be the same. And after this, after the check, in the end, we end up with the same member. Why is that? Have you noticed one thing? You see, let's go back to see this. See here, the load, Lrfv is the load with factors, right? We increase the load because of the uncertainty. in our ASD, we just take the load as it is. Notice that it is 1.5 times different. Okay. Use some dramatic color. 1.5 times different. And notice this. See, the area is the same, but when you calculate the strength, see, also that is 1.5 times different. That is also 1.5 times. So generally, when we use this on the load side, the factored load is generally 1.5 times greater than the service load, which means when you multiply factor of safety with the fee, you always get 1.5. You multiply 5 over 3 with 0.9, you get 1.5. You multiply 2 with 0.75, you get 1.5. This is true as long as the live load to date load ratio does not exceed 3. But that is the magic number behind the concept. And you see, in this example, I deliberately give you the condition where the live load is 3 times greater than the date load. So we write here on the mark to prove that this is how they develop both design approaches. As long as the ratio of live load to date load does not exceed 3, in the end, it doesn't matter which design approach you use, you should always get the same member size. So any question? ASD and Lrfv have hidden relationship. It's not hidden, so they have the relationship. So when folks around here try to mess up with the load combination in Lrfv in Thailand Building Act, they don't want to use the ones that have been statistically developed. It's ruined the relationship that we have here. So when they want to issue their own load combination for Lrfv, that is why I am strongly against it. And all the instructors in steel design field in the country are against it. Somehow we try very hard. I don't know if we are going to succeed in wrestling with this kind of power. But anyway, that's what you should know. If they go ahead and alter the load combination in Lrfv, the so-called Lrfv in this country, and it's not the same as what have been developed, you can't use it because they are going to increase only the load side, but they don't increase anything on the resistance side. If you use the new combination that they perhaps will borrow from concrete, you know, you're gonna have the design in Lrfv with, you know, not so economical at all. And you know, modern economy, it doesn't sound, you know, in engineering perspective. So that's why I suggest that we stick with the ASD, at least for now, because it's the same. But keep in mind one thing: when you're beginning to have a large live load, say it exceeds this ratio, Now it's going to be very clear that if you use Lrfv, you're going to end up with larger sections. And to me, that makes sense. Because, you know, the larger the live load that you have, the more uncertainty that you are going to have for your structure as well, right? And that's what it is, you know. So any question on this? Crystal clear, right? Excellent. So now we move on to the next step. This is exactly what I said. From the first condition where everything is, you know, nicely connected or well all around and so on. Now we have the new condition where, hey, member is going to be spliced. You know, there are so many ways to splice it. And now for, you know, for the sake of convenience, I am going to splice them by using the two plates on top, and I'm going to weld it with 25 centimeters length of weld. And now the condition will arise because we now are going to connect only the flanges. We are going to leave the web exposed. So the shear lag will occur. So you can write down web not connected. Shear lag is going to occur. And that means you are you're going to use A effective equal to U A net. Even though your A net is exactly equal to A gross, but your A effective will now not equal to A net because of this shear lag problem. Okay, and you can obtain more information about this in the spec, but you know, I don't know why I don't have this here, but there are only a few things that you need to know, and I'm going to tell you all here. When you have this condition, they recommend that you treat this as two T's put together. Okay, so we can look at this as two T's. One T like this, and then another T like that. It makes sense in a way because we don't connect the web, right? So when the force comes, they will be forced to split to go to the top and then to go to the bottom. So they will split in half. So basically, we can look at this H as two T's put together. Two T's like that, put together. And so therefore, you know, now your force will have to travel from the centroid of this T section to where the connection is. So that becomes our X bar. Okay. Another thing that you have to be concerned is, say, if you have the channel, this is an extra case. Let's say, is it okay for me to write here, or I should write in the note this one? Okay, I have a picture here. So for the channel, when normally people don't connect the flanges at all. So for the channel, the load will have to travel from its centroid to the connection. So the X bar becomes this. It's not that difficult, right? Now you know. Just two of the most common cases. For the Y flange, you split this as the two T's. And the X bar becomes the distance of the centroid of the T. Now you know, okay? There's nothing more to be worried about. Say, because I understand your feeling when I was your age, you know, when the instructor say this and this and that, and then they say that you would feel like, how am I supposed to know this? You know this and I don't. How am I supposed to know? You're supposed to know this by being in the class, and I'll tell you what you need to know. That's what it is. Okay. So now, with this information in mind, you know that when you don't connect all the elements, you need to check shear lag. And now you know two of the most common cases. I'd say, you know, this will cover pretty much everything. If you run into different cases, you don't know from here, maybe just very, very rare. So you need to bring yourself to read a part of the specification. That's all. Okay. So now we know this. We need to know the section property of the T. So that's why I say I only need to show you this today. So I don't have it on my iPad yet. My apologies. But you can go take a look at the property of the T. So which one to look at? Remember that this is our H150 by 150 by 31.5. Now I may have told you already, or I may have not, but I'm going to tell you again right now that the T is made from cutting this H into two pieces equally. So when you want the information of the T, that T should be cut from this section. So it's going to be T. The first number is the depth, right? So when you cut it in half, it becomes 75 because it is cut. The second one is the width. So you say, now it's not cut in that direction, so it maintains the same number here. And because the last one, because it is cut in half, so the weight should be reduced in half, right? So this should be like 15.75 or 15, say, 8. So you go take a look at the T and you find the X bar from the table, you can carry on. And in this case, the X bar is equal to 1.37 centimeters. Okay. Is there any question, ladies and gentlemen? Hello? Are you awake? Hello?
Yes, sir.
Just one, just you. What about the rest? Your friends still awake?
I think so.
ตื่นแล้วครับ
Okay, ตื่นแล้วครับ So if you say I'm awake now, ตื่นแล้วครับ I'm awake now, it means that before that you are asleep. That's so sad here. Okay, anyway, just kidding. I think it's time for you guys to have another break. And this is the second break. So let's take 15 minutes, okay? So that you have more time to refresh yourselves, to recuperate, to gather your strength. So we'll meet around 10:35 then.